In several situations, we encounter both conduction and convection resistances to, to heat transfer. And let's suppose we have here a solid wall separating two streams of fluid. So let's say we have this solid with the thickness of delta X that's separating two streams of fluids. One of them is hot, or let's say this is the hot stream, and the other one is cold from both sides of the wall. Assume, let's say this is temperature TWH on the hot side, and this is TW on the cold side. And let's assume the temperature of the hot fluid H. This is TH, so this hot fluid coming with the temperature of TH, and the same thing, this cold fluid coming with the temperature of TC. Then we have such temporal distributions here. This is going to be TC, and inside, for the case of we have a steady state conditions, no heat generations, you're going to get the linear profile for the temperature distributions from T of wall hot and T of W of wall cold. Now, what we have here is we have a resistance, convective resistance here. So here what happens first, we have convection, then conduction through solid, and then we have convection. So heat is getting convected in. So we have Q of convection here that brings heat to the solid. The heat is propagated through the solid by conduction, and then taking out of the solid by convection. So we have three forms or three stages of heat transfer or resistances. So we have convection, and convection resistances against the heat flowing from the hotter side to the colder side. So at a steady state condition, no heat generation, if you start from the energy balance equation, we would get heat in is equal to heat out. So what we are gonna get here is Q, this Q of convection and conduction, all over the stages are gonna be the same. So what we can write here, Q is gonna be like, let's say for the convection that happens here is gonna be Newton law of cooling, which is gonna be, let's say, H1 A TH minus TWH, and this flow is going to be equal exactly to the conduction, which is KA over delta X TWH minus TW of cold, and this is going to be exactly similar to the heat flowing out by convection, which is H2A TW of cold minus T of cold, temperature of cold. Now, if I rewrite this equation based on the temperature differences, it's going to be TH minus TWH, which is going to be Q over H1A, and TWH minus TWC is going to be Q divided by Ka over delta X, and Tw of cold minus T of cold is going to be Q over H2A. If I do the summation of those, or like let's say before doing that, I can just write that one exactly based on the resistances for electrical current. We have one convection, and then another convection. So the temperatures here are known, TH and TC, the stream temperatures are known. The wall temperature may or may not be known. Now this one, the resistance for the first one is going to be based on the equations that we have, is going to be 1 over H1A. For the conduction is going to be delta X over Ka, and here is going to be 1 over H2A. So if I just do the summation of all of them, what we are going to get, if we add them, what we are going to get here is T of hot stream minus T of cold stream is going to be Q 1 over H1A plus delta X over Ka plus 1 over H2A. Or the other way that we can write this one is Q is equal to 1 over H1 plus delta X over K plus 1 over H2 to the power of minus 1 A T of H minus T of cold. So we are trying to formulate that similar to what we have seen for Newton's law of cooling. Now let's call this one, this property U is 1 over H1 delta X over K 1 over H2 to the power minus 1. And if we call that one U, then Q is going to be UA TH minus TC, or TH minus TC 1 over UA. Okay. Now what we call this U is the overall heat transfer coefficient. It has a unit similar to H, the transfer coefficient, watt per meter square Kelvin. And let's say if the solid surface is a tube, let's say is a tube, then we can use the cylindrical coordinate, and then what we are going to get here is Q is going to be, let's say, TH minus TC divided by 1 over HI AI plus natural log of RO RI divided by 2 pi KL plus 1 over HO AO, where AI is 2 pi RIL, AO is 2 pi ROL, and L is length of tube that we have. This situation can be very useful when we are designing heat exchangers. I will talk about this. So we can write out the U based on different, like here we can find out what is the U, the overall heat transfer coefficient. I'm gonna label it as UI, and here UI is gonna be 1 over HI plus AI log of RO 2 pi KL plus AI HO AO. And this is the UI, is the heat transfer coefficient U based on the inside tube area. Of course, we can have it based on the outside. So I can have UO, which is 1 over AO HI AI plus AO natural log of RO over RI 2 pi KL plus 1 over HO. So this is based on the outside diameters, and generally these type of calculations, I can write it down. Is very helpful in heat exchanger design. So for a typical, let's say, shell and tube heat exchanger, what we have here is we have a bigger pipe or a big cylinder, something like that. So we have a big cylinder that there is some stream for let's say hot flow in, and there is another internal tube, one or more than one, that is passing through. So we can have internal tube for the shell and tube, and this could hold the cold flow. So we could have, let's say, cold flow in and cold flow out. We can have hot fluid in and hot fluid out. So you would see, like, we have this tube. Actually, there are two sort of tubes here, but there is an internal and external flow to that one. And let's say this is length of L. And we can use this one for many calculations. We will have a lot of examples on that. So note that when we are writing this overall heat transfer coefficient based on UI and UO, they are essentially the same thing. It's just like being the ratio, they're being adjusted by the ratio of the area. So Q, can write it based on the internal. If we're using internal, UI AI TH minus TC, which is equal to UOAO TH minus TC. Now, in other words, UI AI is equal to UOAO, or UI is AO over AI UO. And since this is obvious, but since, let's say, AO over AI is greater than 1, then what we have here, generally UO is UI always is less than UO.